So hello, everyone. It is really a great pleasure to be here, which is the last session of this whole symposium on wood life that was organized in collaboration with institutions of Turkey and Sweden. We are really very happy to have different topics to discuss from the very beginning of this symposium. And finally, we are in the last session of this whole event, which is named as Innovation and Future Possibilities. And we have speakers from diverse fields with different topics to be discussed in this session. The major emphasis of this session will be computational design and digital manufacturing methods used in design education and industry, as well as technologies for treatment of wood as a material that made a complete new structure idea possible for upcoming features of timber construction too. So I would like to welcome you all, and I would like to welcome all the speakers that are joining us for this session. And to be, precise with timing, I would like to begin with our presentations. As you see in the program, we will be proceeding from the program session to proceed. And our first speaker will be Anna Maria Oru. She's an architect and she's an affiliated senior lecturer also in Construct University of Arts, Crafts and Design. And welcome, Anna. We are really very curious to hear from you on biomimicry and nature as a source of inspiration and nature's innovation for us. And thank you for coming and joining.
Great, thank you very much for having me. So I'll be talking less about digitalization, but more about nature. And I've been asked to come and entangle the wood life symposium thinking with biomimicry. So this might be a new word to some of you, but let's see if we can get through to it in 10 minutes. So we are part of a vibrant and dynamic ecosystem, and there are over 30 million other species on the planet today besides humans. We're part of a connected and vast array of habitats, and biomimicry can show a way in which to understand, learn from, respect, and belong to this larger ecosystem and get a lot of ideas from as well. So what is biomimicry? It comes from the word bios, which means life, and mimesis, which means to imitate. And Janine Benyu states that it's a science that studies nature's best ideas and then imitates these designs and processes to solve human problems. And so nature has had 4.6 billion years of trial and error to figure out ways to innovate, to design sustainably. And she can answer challenges like how can we feed ourselves? How can we create regenerative cities and buildings that react with the environment, particularly by forest innovations, and how to planetary boundaries. So in biomimicry, nature is seen as a mentor, as a measure, and as a model. And as a mentor, we start to view and value nature based on what we can learn from nature, not extract from it. As a measure, we use an ecological measuring standard, living within the land's capital. And as a model, we can start to look on a form, a process, and a systems level for strategies to solve any kind of design challenge that you might think up. So where can you go to? Well, in 2018, we released a report with my co-authors, Torben in Denmark and Lily in Finland, on the Nordic forerunners in biomimicry, commissioned by the Nordic Council of Ministers. And this, basically out of the study, we recommended a hub, a place that gathers the people, the knowledge and the expertise to learn more about bio-related fields. During an 8-month period, we sort of mapped actors in biomimicry and bio-related fields in the Nordics and in the EU. And we've also been informed that actually biomimicry activity is taking place in both Turkey and Cyprus. And these seem to be in very early stages though. So here we have some wood-related examples from some of the actors, the Wallenberg Wood Science Center, Umeå Plant Science Center, OrganoClick and Tree Search. So Wallenberg Wood Science Center, for example, is a research center with a focus on new materials from trees. They create knowledge and build competence around these kind of innovative ideas from forest raw materials. And tree search, for example, is research on new materials from the forest. And finally, this is our center. We have the Nordic Biomimicry Center, which was launched in 2020, and it's a knowledge hub and education platform for this way of learning from nature-inspired strategies. And it was founded by myself, Frederick Mobay, and Louise Hordorf-Skjeggestad, who work closely with the Stockholm Resilience Center. But we have Nordic partners in Denmark, Norway, Finland, and also Iceland. So our aim is to provide these kind of opportunities for network and learning biomimicry and connecting to others and bringing new research forward. So biomimicry is well known for its use to self-design ideas both creatively and sustainably. And in a moment, I'll go through 3 categories, but just first, some more outline of opportunities to learn from nature for built environment applications, for example. These are 7 categories for these kinds of applications from nature that you can use in architecture and urbanism, and they come from Michael Pollan's book on biomimicry and architecture. I worked with Michael for a number of years at Grimshaw Architects in London, and then helped him establish the new studio Exploration Architecture, where many of the projects that are shown in the book are actually from our work we did together during this period. So here, if we just look at the 7 areas, we can learn from nature how to build more efficient structures, how to manufacture different materials, how to create zero waste systems, how to manage different kinds of resources, especially water, how to control internal environments, and how to learn about both lighting and energy strategies. And I can assure you that the forests hold strategies for each of these areas. You just need to look with eyes wide open and put on your biomimicry glasses. So the 3 sort of themes, because of our lack of time, is nature helps to solve challenges and innovations of ventilation, for example. The humidity sensitive scales of pine cones, open in dry conditions and close in damp ones. And this hygroscopic behavior allows them to be in relation with the environment. The cone strategy has already inspired different kinds of textile design, facade design, and so forth. Here we have design inspired by the spruce cone. The design is by architect Achim Menges, Professor of Computational Design at the University of Stuttgart in Germany. And he has created a climate-responsive architectural skin that can alter its shape passively through close reading of the environment's condition, just like the cone, rather than using conventional tech applications such as sensors, motors, and so forth. This is the Hygroskin meteorosensitive pavilion. And he developed this kind of climate-responsive wood made from carefully engineered fine plywood sheets. Nature can also teach us how to create efficient and effective forms using very little or no energy at all, and uses only material that it needs put into the right place. Nature uses about 5% energy to realize its natural structures, and humans tend to use 70% or even more. And so by using shape and putting material where it needs to be most, we can definitely learn from nature in this area. And there are sort of methods in nature for creating shape, such as folding, plants for planar surfaces like the Australian fan palm, ribbing such as the Amazon water lily with a stiff underside, twisting, shells, and even tree trunks use vaulting for stiffness. Layering, the abalone shells also use layers of hard and soft discs to stop cracks from propagating. Inflating, like the frigate bird's throat pouch that carries food, and collapsing. Peacocks have these fantastic, deplorable, collapsible tail of feathers that expand and contract so elegantly. And finally, nature knows how to share resources. Forest root systems are a wonderful example to mimic that share and transfer resources, nutrients, and water throughout the forest ground. And cities that function and perform like forests are a good example for exploring this crossing between biomimicry and urban systems. What are ways of learning is one space, but there are other ways through different kinds of pedagogy, staging events, and exhibition. So recently in Copenhagen, we ran the Biomimicry Festival, basically an adventure in what biomimicry can teach us. And it's about really meeting nature in different ways that we are not used to, and reconnecting back to nature in new modes in order to find value in this. We run many workshops, universities, government officials, also different kinds of companies that have specific kind of challenges. Also, exhibitions are a way. I believe Jonas and I are both participating in this current exhibition at Fabriken, which is a contemporary art and architecture center in Stockholm. And the work here is showcased from my students on a course I ran back in the spring on biomimicry and industrial design. And also, very often I try to take biomimicry and being in contact with nature, and very often we have these kind of encounters in forests and in nature, where you start to experience nature through your sensorial system, through embodied encounters. So finding other tools of understanding materiality. It's usually done through a Japanese choreography called Buto. And here, for example, we were trying to understand stone, but you could, of course, translate a lot of these experiences and these interventions by starting to understand different kinds of woods. Here we have a few more images. So what are the resources available out there? One is, of course, our hub, and here we also have many resources under learning, books and podcasts and different kinds of videos that you can tap into further if you want to know more. Asknature.org is an amazing knowledge source from the Biomimicry Institute, something I've used extensively since 2003, since I embarked on this journey. But I'm warning you, you might lose a lot of hours. You sort of get lost, and I'm very interested in this maze of nature's knowledge. And there are many, many books out there for the Swedish-speaking audience. Lately, a book published by Fredrik Moberg just this year, the first comprehensive book in Swedish on biomimicry. So I want to leave you with 3 takeaways, if anything, that you remember from today. Create conditions conducive to life, just like the Wood Wide Web does. Achieve true sustainability by mimicking nature in your teams, your ideas, and the relationships that you forge ahead towards life-affirming goals. Play, bring creativity into your organization and practices. Rilke said that the future must enter inside you long before it happens. So use your imagination to create a more sustainable future and working culture. And biomimicry can be a first step to that future, because nature really offers a storehouse of ideas. And 3, go outside, engage and learn to observe nature in other ways, create personal contributions and meet species in new ways. My threshold has been through beekeeping and olive tree keeping, but you'll have to find yours. So I finish and leave you with the most important question to ask in this moment. What would nature do here? Why or why not? We are a young species still trying to get things right, and nature has all this 4.6 billion years of knowledge we could tap into. So thank you very much, and may your path continue with nature at your side.
Thank you so much, Anna, for this both a quite broad view on nature that you introduced for us, and how we may perhaps engage ourselves in nature for our design thinking and creative approaches at the same time too. Thank you so much. For this panel, we may have questions after each presentation. So if we may have any questions, we may just have them from chat or the other mediums that you may just ask your questions to. Okay, I think we do not have questions at the moment. Perhaps proceeding with the panel. If we have further questions, we may go back and take answers from you, Anna. Thank you so much. It was very inspiring.
Thank you very much.
And as a second speaker, we have Jonas Runberger. He's an architect also. He's an artistic professor in digital design at the Department of Architecture and Civil Engineering in Chalmers, University of Technology. And he also will be providing us a different perspective on digital matter and timber architecture at the intersection of research and practice. Thank you so much for joining in, Jonas. And we are very curious about your topic too. Welcome.
Thank you. As always, Anna-Maria is a hard act to follow. I've been following her progress and development for many years, and I need to get more my head into that field as well. As maybe a present at some point in the work I want to present. So what I wanted to do is to go a quite fast journey through a number of projects and work done at, as I see it, intersection of research and practice. So in many cases, there are actual architectural projects. In others, they are more, let's say, speculative and explorative. And I'll step right into it. We have a short time, so I'll just go through this project and make the story as it unfolds. So I want to start with being in the forest in a certain way with a project that deals with a pedestrian bridge, something we worked with at White Architecture a few years ago. And what's interesting here was that it's part of a landscape commission. So it's at the site in fairly southern parts of Stockholm, where this bridge is planned to pass over a quite heavy traffic road, train lines, etc. And it makes a shift and turn because it also has to climb up a hill. So that was a given condition. And when we met this site, we also realized that this little shift that was needed to extend the length of the bridge actually passed through a grove of trees. Among many were oak trees. In Sweden, oaks are protected. You're not allowed to cut them down. They're valued high. And in general, of course, we wanted to be able to do this project without interfering too much with this quite beautiful site and the valuable ecosystem. So we try to understand, let's say, the form and obstacles and the locations of every tree here, and set that up into our design models as a given parameter, combined it with previous listings of individual trees, and that gave us an opportunity to at first find a location, a specific location for the bridge through many iterations and following, of course, computational workflows. The most important was actually to understand the site here. So we know everything except for, unfortunately, the roots of the trees, which hopefully can be investigated later. After setting down this location, we also started to look at how the bridge would be structured. And we had a fortunate situation where we had a researcher on glulam timber with us from a collaboration with the European research project. So we managed to, again, many iterations to, at a very early stage, come up with a solution that we thought would be both efficient, using timber, and also, well, beautiful, we think. And setting up a construction system, also in a dialogue with the producer, Bloomer Lehmann, allowed us to understand the conditions for glulam fabrication at this scale and in these forms. Here we also could integrate certain analytical systems and simulation to understand the extreme curvature of the bridges. And at some point we decided that the research aspect of this project and the practice aspect would diverge from each other. So to take certain questions even further, our collaborator Tom Svilands from KDK Sita in Copenhagen pushed certain ideas forward. So we, on our end, we have a functional, viable structural system. On his end, he's trying to push the limits. And I think this relation between research projects and actual projects is something that interests me quite a lot. And he could also then take the step to go towards materiality. On one hand, to simulate it, understand how things were structured, and on the other, also understand the performance of the actual timber and actually build a mock-up. Also investigating alternate ways of lamination and so on. So this journey continued in parallel. This was done while we did the final touches of the design of the bridge. And then finally presented in an exhibition. Now, this is obviously a very small part of a bridge, but for an architect in practice, this kind of physical mock-ups are very hard to do. We do a lot of models, but to actually understand the material behavior and performance of wood to that extent was extremely valuable. So this project kind of combine these different aspects and is still living and hopefully will be completed, but it's still an example of something that we pushed. This also gave led us in a direction that we did not expect. In my team, we worked with at many different scales and with many different kinds of projects, but we've landed now in bridges, and bridges are of course interesting because they, on one hand, they're kind of clear in their structures and the principles. On the other hand, they allow thinking of materiality quite carefully, and also they are contextual. So this is an example of a competition entry a few years ago over hanging bridge, actually quite close to the other bridge location in southern Stockholm, where we also could explore ways of making, but primarily at the schematic level, the whole structure of the bridge. Unfortunately, I take the opportunity to say they decided for a concrete bridge because they felt it was more inclined or better suited to the site, which is something that still puzzles me. But this bridge projects have continued, and the most recent one, which actually was completed yesterday, is an ongoing or a commission for Umeå, where 4 bridges will be planned in parallel or are being planned. And we obviously saw and took this opportunity to, you can see to the left are the longer bridges. They are in steel, so I will leave them completely out of the picture. But we took the opportunity to propose alternative bridge types in timber here with distances for over 200 meters. So this is what in Swedish is called sprängverksbro with these supports. The oldest car bridge in timber in Sweden has this principle. It's a few hundred years old. But we are really interested in trying to catch up also and on conventional and historical understanding of structures for bridges and these materials. And this is of course coming more and more. Through these projects, we're trying to push these boundaries, which also means that you can't do small scale experiments in glulam. You need to think about the future construction and building, such as the work in this cable steel bridge. But I will leave the bridges behind for a second and try to connect the dots in the end. I also wanted to talk about another project where primarily it's been done in academia, the Woodward Project, which really deals with the thought of using additive manufacturing with cellulose-based materials to use the leftovers from the timber industry. So this was done with many different partners, but this particular case of the project was done with students at Chalmers, architectural students, who designed a lightweight rooftop extension project having these techniques in mind. And what was interesting was to shift between sort of a conceptual attitude and very spatial and, let's say, aesthetic approach in trying to push the boundaries of making while creating quite emotive spaces. So this was one of the proposals that was pushed furthest, where the students also have to try to understand what does it mean to use these technologies. How do you have to think about construction and structure and modularity and things like this? Starting with models with small scale desktop 3D printers and testing that, and then realizing that when you go up in scale, you have to shift and understand how materials actually behave, even controlling the tool paths of the robots through scripting in different ways, and simulating a process in the end, understanding, well, the quantitative aspects of the work as well, and finally moving to a full-scale production. So this was sort of an achievement done during the run of one course, from no understanding at all to completing a full-scale mock-up and mounting it and putting it on display. This is work that continues now in additional research projects, but this was for us a bit of our own internal landmark. And I wanted to wrap up with my own ambitions to try to tie these knots together and see how these different approaches can work together. So this is a conceptual and speculative research project called Interstitial Towers. And it has a lot of parallel agendas, and was developed within a broader research project called Beyond Efficiency. And it's actually on display in the exhibition that Anna Maria was mentioning before. So it looks at residual spaces in the city, and it suggests a sort of a new kind of typology, which really takes very little space. It has a small footprint, the project so far has been recently published as well as part of the Beyond Efficiency project. But it's on one hand working at almost a regional scale with identifying locations and so on, and then just to give an idea of site and size. Sorry. The towers would be placed at this sort of at an intermittent scale between buildings and maybe even sculptures. This is actually a view from my kitchen window. And then playing around with the ideas of programming these elements that you could actually use them, greenhouses, water purification, solar, heliostats, all of these things, builds up a narrative of something that maybe could be beneficial. So the project has included not only sort of an aesthetic exploration or structural principles, but also trying to add technologies and other things that in the end could actually have a social function also. And what's interesting for me is that it's been going through iterations. This is from that exhibition Anna Maria mentioned, and worked out in models to even bigger models and try to understand these principles. And what's really interesting has also been to think about the ways of construction here. There's an idea of, for instance, the reference to barn racing, like in the US and elsewhere, and how could this actually be done in a low-tech version and combine high-tech principles. So the project at this point is still living, and I believe it actually will start to thrive, because now we're selected 3 towers that will be produced by combining these approaches: additive manufacturing, the glue lamp principles, robotic production, etc. And downsides are, well, our ambition is now for next year to have mock-ups at the scale, which could test more things. And this is a bit of an announcement. The plan is to exhibit this at the H22 City Expo in Helsingborg in Sweden in May next year. We are still looking for potential collaborators, so I take that opportunity as well. But that's sort of a cut through a section of what I'm up to at the moment, and trying to tie loose ends together in different ways. So thank you very much.
Thank you so much, Jonas. It was very interesting, 3 different projects and 3 different approaches, going from different scales, and especially the interstitial towers, where you really reduce the footprints of these tower ideas and turning them into different kind of both structure, construction, and a material research at the same time, which might be put into practice. It's really very interesting, and hoping to see it in the exhibition that we are planning to have it.
Thank you.
I'm again checking for the questions, but at the moment I think the audience is warming up at the moment still with the topic and the subject, and perhaps if we may proceed with the presentations as we go further, I believe we will be having questions in the topics that we are just clarifying in our presentations. So we may just proceed. The next presentation that we will have is by Ardeshir Talaei and Hazal Yılmaz. Ardeshir is a PhD candidate in the University of Calgary, and Hazal is also an interior architect and co-founder of Rolab studio, and she has a research again on material systems too. So welcome, Ardeshir and Hazal. We are really again very curious about your topic too, on Catalan architecture and how we may recycle the timber works in Catalan architecture. So please, welcome.
Hello, everyone. Thank you. I will be sharing the screen. Oops. Okay, so first, hello, everyone. This is me, Hazal Yılmaz, and we will be presenting with Ardeshir Talaei. So Still Alive is a project which is developed in IEC, Master in Robotics and Advanced Construction program by me and Ardeshir. Wood has been used in construction for thousands of years and is still one of the most widely used materials. And nowadays it is popularized because of the sustainability factors as a carbon storage unit. However, wood is the second largest component of construction. Construction waste material refers to the material that cannot be used for standard purposes and must be removed. Besides the cost, wood waste also affects the environment. The wastes represent a major problem for the environment, like the air pollution, CO2 emission, and etc. One of the current solutions for wood waste is to throw them in landfill. If recyclable material are put into landfill sites, you use more energy and resources trying to create new materials instead of reusing or recycling. So landfill sites should not be the first port of the call for reusable or recyclable materials. Other option is recycling. Recycling process is a process of converting waste material into new material and objects. It is an alternative to conventional waste disposal that can save the material and help lower greenhouse gas emission. But the problem about recycling is to require another factory, which means that also problem for energy consumption because of the transportation and chemical processes. Because of that, we are proposing upcycling instead of recycling. The goal of upcycling is to prevent wasting potentially useful materials by making use of existing one. By doing that, we can have less energy consumption than recycling, because during the recycling process, we need another factory and transportation, which also causes the CO2 emission. By having upcycler process, we can integrate all processes into one factory or let's say one workspace. And also it reduces the consumption of new material when creating new products. So current upcycling process includes standardization. To do that, they recut waste material into a standard geometry. Apart from energy consumption and cost, the standardization process, it also creates problem like having another waste material during the process. So we are trying to revise this process by taking reference from Hook Park. In Hook Park, they're using raw material by its own shape. Rather than cutting them standard shapes, they are designing the process based on the natural geometry of the raw materials. So Still Alive is the new waste solution to transform non-standard material of waste into a new resource. We are proposing to the same method, applying that to natural wood. We can also apply the same methodology to waste as a kind of non-standardization. By doing that, we are introducing to waste as its own to design process. By having a non-standard process, we can reduce the amount of waste, and also we can use the new waste material as an input for non-standard design process. To demonstrate this process, we collect the waste material from a CNC workshop. Then we generate an arbitrary free-form surfaces as an example of non-standard design. A solution to connect these two in producing the service between the waste and design as an input. So Still Alive is a database process to produce new solutions from waste material. Using computer vision, autonomous fabrication, robotics, and generative design process, our aim to convert existing waste material to a resource based on the upcycling process. So our solution is adding value on the waste material through a process of autonomous 3D scanning and robotics. First, we scan every piece of material to get to know the properties about the waste, and then we develop an algorithm to design for manufacturing and assembly. For the final step, we integrate non-standard waste material and non-standard design with robotic fabrication technology. So for the process, in a non-standard process, each piece is unique. So first we need to know our material to extract data from it. Therefore, we need to scan every pieces of material. So first we put all the pieces into black fabric. Then we extract the information into a database by autonomous scanning and computer vision. Using a robotic arm to find the scrap and extract the data through the remote sensing, saving into a database and sorting the physical material through pick and place process. By doing that, we can have live database constantly being updated with the robotic arm. And we use KUKA-EVA robot with the remote sensor and SCG gripper. The problem with the robotic fabrication process, we should manually locate and calibrate the pieces and give this data to the robot, which is time consuming and also not practical with the big amount of the pieces. With the autonomous scanning system, robot can calculate the size, shapes, and thicknesses by itself. And also we create the gripping strategy, means that robot can find the pieces without calibrating each pieces manually one by one, and also can calculate the center of the pieces to pick them up. Ardeshir will be continue.
Okay, thank you. As Hazal explained, we collect enough information about the material so that we can claim that we know our material and we know enough information and properties of this non-standard material that we have. But then the second challenge that we face is basically how to use this data and how to use this information and properties in our design process. Here we will be presenting a simplified version because normally there's so many like edge cases and exception handlings that we don't have time to go through. But if we take a look back at the diagram, so through the scanning process, we kind of handled the left side of the diagram, and on the right side, we are trying to basically revisit the design, considering all the properties that we have already extracted. So the first step would be basically to tessellate this freeform surface that we just took as an example of a non-standard design and tessellate it into some planar pieces so that we can fabricate it. For this reason, we chose an algorithm called tangent planes intersection. Tangent plane intersection, or like TPI for short, is basically a very well-known method for tessellation, and we chose it for some specific properties of it. These properties being, like if you want to implement this, the first property is it's easy to implement. So if you have a freeform surface, as the one that we have here, the first step is to place some points on top of the plane. It's just randomly distributing, or maybe not randomly, but very symmetrically distributing points on the surface. The next step is to calculate the tangent plane to the surface at every of these points. And then you can simply calculate the intersection between these tangent planes, and you will end up with a tessellation system. Apart from this, that it's easy to implement, it has some very flexible properties as well. The first part of this is that you can easily define the number of the planes you're going to use. As you can see in this slide, you can have very few plates, or you can have very much smaller plates to basically make up your tessellation, to let's say interpolate your freeform surface into some planar pieces. The second property, which is also very useful for us, is that it's really reconfigurable. Like you can keep playing with how you place these points on the surface. You can have different configuration of the points, and you will end up with very different tessellations and very different type of panels. The third property is that you can modify it partially. You can control and you can modify a very small piece of the surface without affecting the whole tessellation. So the whole point I'm trying to make here is that this system is a very flexible system of tessellation. And this lets us implement, or basically this lets us to integrate this other data that we have collected through the scanning process into our design step. So after the tessellation, we are up with the panels that we have. And the next task is that, okay, we want to fabricate this through the material pieces that we collected, through the waste materials that we collected. So that's a problem of nesting the pieces into those material pieces first. So for that, we had to come up with an automated way to basically nest the pieces into the scrap materials. And we just decided that we probably don't want to fully nest the pieces into each other. So the only goal that we are following in this demonstration is to assemble this structure. Like we don't really care if we have holes in the middle, or if we have, if you are losing some parts of the final pavilion or whatever we name it. So actually, previous slide. Sorry.
Yeah, previous slide.
Yeah. So what we did is we used the same strategy that we designed for gripping. Like we had this algorithm that the robot can automatically calculate some kind of gripping strategy to pick the piece up. And this algorithm includes using some points and defining some specific points. And then we have this customized nesting algorithm that kind of finds a way to fit all those points into some polygon that we defined. And in this case, we defined the polygon as the material piece that we have. And we also defined some critical points on the panels that we have designed, and we use the same algorithm to fit them together. However, like points are not enough for defining like the critical portions of the panels that we have designed. So we want to extend this to defining some specific lines and patches on the panels that we have designed, and want to make sure that those are all cutted through the material, like we will have material on those places. To extend this, we use Minkowski algorithm, which is an algorithm like it's like arithmetic operations, but on polygons. You can add polygons together or subtract them from each other. So what we did is we basically used this algorithm to convert all the lines and patches into points again, and then use the same algorithm. And anyway, we came up with this custom nesting algorithm that you can see one example here. We have this triangle on the left, and we have that target piece on the right. And we defined some specific lines, which you can see as like thicker lines on the panel. And this custom algorithm just fits your panel inside the target, which is your material piece, in a way that like all those lines lay inside the material. So after we managed to nest the pieces into each other, then we probably have to evaluate to see how well these things are being matched together, like how well of a fitting we are achieving. So for that, we defined a lot of numeric criteria in terms of, for example, what is the upcycling rate? Like how much of that material that we had, how much of it we are reusing and we are upcycling, or things like how much of basically the panel that we have designed, we are losing through the nesting process. So after defining a lot of criteria, numerical criteria, then we have an automatic algorithm to nest the pieces, and we have some very specific criteria. So we can something like this table that you can see, much bigger than this. This is just a small example of the table, that we can start checking all the panels against all the material pieces to see which one fits into which. And we can also evaluate to see how well these two fit into each other. So the point is to find a solution to basically fabricate these designed panels from the non-standard waste materials that we have. So after coming up with this table, we need to come up with a way to decide, okay, we know all the information, we know which panels fit into which and how well they fit into each other, but then we have to make a decision to which panel should be made from which piece of material. We are just branching into another field, which is linear programming, a sub-branch of mathematics. And then there's this very nice algorithm there now known as Hungarian method or Munkres method, which you can use for optimizing this kind of assignment problems. So then we use this problem. And so by this point, this is where things start to get interesting. We have an automatic algorithm to tessellate the freeform surface into some planar panels. Then we also have another algorithm that we can check to see how well these panels that we have designed fit into the material pieces that we have, which is another challenge. And we have another algorithm to do that automatically. We also have some evaluation criteria to see how well we are doing on basically matching the panels with the materials. And since we have all of this automated, all we need to come up with is the right configuration of the tessellation pieces that will result in the best system for us. And well, this is normally a very complicated problem, but then that's where we can basically use the computers and all the processing powers they bring us. So we turned into evolutionary algorithms. We have all these algorithms that can automatically tessellate, fit, and evaluate the system. We feed all of this into an evolutionary algorithm, into an evolutionary solver. And the evolutionary solver, as you can see in the next slide, will keep iterating through different configurations of the tessellation, testing every each of them. And well, it's not totally randomly in an evolutionary system, but through testing and testing and testing and collecting the evaluation data from each of the tests, we will end up with maybe not the best result, but at least a very good result. So through this process, by designing all these pieces, we managed to basically create 85% of the initial surface that we have designed. And we managed to reuse around 66% of the waste material that we had to make sure that this whole thing is working and to start like walking into the materializing part. We also cutted the pieces, like we physically cutted the pieces through a robotic fabrication process, but then we never assembled them really because there was one big part missing, which is the joinery system. Like how are we going to join these pieces together? So the point is that we have already branched into so many different fields. Like we have robotics here, we have AI in terms of computer vision and evolutionary algorithms. We use a lot of mathematical algorithms and operations. And well, this was developed during a course of 2 months. So that's as far as we could get in this project. However, this project is yet ongoing. And we are still working on different parts of it, especially the joinery part. And hopefully this can basically get somewhere in the close future. There's also a short video that
yeah, if we have time, we have also 1 minute video, but if you don't have time, it's okay.
No, since we have time from questions that we couldn't use, perhaps we may watch the video.
Okay, so we have, of course, problem with the sound, but okay.
So through this process of scanning and then using all those data from the scanning system, just so what you see here is basically an autonomous scanning system. We have all the scanning system on top of the robot. The robot detects the piece, like extracts a lot of information, including the shape, the thickness, the color, the grain direction, the weight and everything, automatically picks the piece up. And since we have everything already pre-calculated and automatic, the robot knows what shape is supposed to turn this piece into. So we also have, this is like a mock-up system. It's just we are using a very simple router to cut the pieces. And so the robot automatically picks up the piece, cuts it, and then stacks them at some specific place. Ideally, the robot could also help us assemble the pieces together, but when we didn't have the joinery system. So
that's all. Do you have any question?
Thank you so much.
Thank you.
Thank you really so much. It was really very interesting to see both how our, let's say, relation with wood as a material in special and as with an idea of upcycling, how you may really utilize the technologies, especially the computational technologies, and our prospect to looking at the materials too. And since wood and timber is a very valuable and at the same time organic materials, how we may upcycle them. And it's very interesting to hear that you said, Ardeshir, 66% of the waste material is used and 80% of the surface is kind of covered with this material, as far as I could notice. Is it like that?
Yeah, exactly, yes. It was 85 actually.
85.
Credit for that extra 5%.
Well, it's really very promising.
Yeah, this is the whole point is that we are using mostly the same machinery and the same technology that you can find in a normal wood workshop, right? Like we are using this slick piece of technology, which is the EVA robot, but then that can be also implemented using a normal robot arm. That was the whole point of this. Like we don't need to spend a lot of energy and spend a lot of time on basically upcycling the wood. So that was the most interesting part of the project for me, at least.
Yeah, very interesting. And we have a question from Ece Çakıray'dan. Have you guys had a chance to start a dialogue with the industry about your research? She asks.
Well, we tried a few times. Like this project, as I mentioned, is still in development. There are, like this was a simplified version because normally when you're actually trying to implement this on some material that we really collected the material from a CNC shop. So there are a lot of unknown parts. There are cracks. There are some pieces that are too small, too big. So there are a lot of exceptions. There are a lot of edge conditions that you really need to take care of. There are a lot of special cases. So the project is much more complicated, and we're still dealing with these complications. We're kind of waiting to solve these complications before reaching out to the industry for actually, I don't know, implementing this project in a real world scenario. But yeah, that's something we have planned for, at least.
Yeah, as a perhaps future plan or future prospect of this, research that you just completed. Really very interesting. Thank you so much.
Thank you.
Thank you. And I think it's all with the questions too. Now, as next presentation. We have, in fact, Ekin Arslan. She's a senior architect and a designer also. She will be presenting a project, in fact, from design education side of the panel. And for this design education side, I will be presenting very briefly about the computation-based basic design studio that she developed her design with her team of friends also, where we try to develop a certain position both on computational technologies, design and production and manufacturing at the very early year, at the very first year of the design education. I will be very quickly and very briefly try to have a introduction to the studio topics that we were going through to perhaps have a further understanding of Ekin's project and Ekin's presentation too. So what was that studio is about? What is computation-based basic design studio at Bilgi University as a first-year design studio where different disciplines of architecture, interior design, and industrial design department students are coming together. The basic, perhaps, target and the basic approach of the studio is bringing design and manufacture together, but with a deep concern and awareness for the materials, for the technologies, environments, and the problems that are very near to us at the same time. So though computation is the very forefront of the studio name, the basic intention is to develop a kind of a logic where students begin to realize that they are part of a larger whole and larger network of things, in fact, while just developing their idea on design subjects and topics. So this is a big studio, in fact, with teams of instructors working together. And it started at 2009 and now developing at the same time. Want to introduce in one-to-one scale production and manufacturing procedures into the design education is one of the important prospects in the studio, but it is also a studio of research on design, or research by design studio, where material research on technology, design, geometry, material and production processes is introduced. So I will go very quick from this part on to just have space for Ekin more. These are the topics, and these are some of the projects developed to, just improve the design skills and understanding skills and logics of the students. And this is parts and whole relation, where they may begin to perceive the more larger network of things in broader perspectives through the studio, through the concepts and material research and the design problems that they are working on. And each and every stage, all the design problems are formulated in a way that they are turning into one-to-one scale products. At the first semester, it is the lanterns are the final products of the students. They're working in groups, in collaboration, and they put their works as lanterns in the environment, in the campus, in the interior design of the studio. The pandemic period, they place their work at their home and so forth. So it goes on like that. I may go in detail in another talk about the studio, but at the final stage of 1 year of study at this first year education, students go through both material research, geometrical research, and research by design procedures, and produce their projects at one-to-one scale. By beginning to figure out the potentials of the material that they are working on and how they may solve out certain details to develop them into self-carrying structures too. So timber and wood is mostly an important part of our studio too. There are numbers of projects that we developed in this studio, since this is a crowded studio of mostly about 200 students, and like 20 instructors at the same time, and all the instructors are dealing with this research topic of mostly design research, computational technologies, so, and geometry, design computing too. So within that prospect, this is a very quick overview of what we have been doing in the studio. In this perspective, what we will be focusing on too as a product of this studio is this little tiny project that you see here that we developed at 2013 with the group of Ekin, where they were working on plywood and how to test its performance and behavior, turn it into a shell-like structure just by using only plywood as a material and an interlocking system at the same time through a more parametric and computational approaches where only a certain geometrical and construction-wise, surface-wise logic is developed, where it might be adapted to different situations and to different sites and to different scales and sizes at the same time. So at 2018, we had an invitation from Venice Biennale as a university. And in the university, we decided to attend to that Biennale by the work of Karapace that Ekin will be going to just present us here. These are some of the other timber works that we have done under the type of urban furniture. Students mostly work in groups in these, and both the material properties, geometrical possibilities, and the detailing of the material is worked in detail in about 5 weeks or so. And this is a very, let me say, introduction of the studio. And now perhaps to understand a bit more and deeper about one of the projects that we developed within this studio, conception is what Ekin will be presenting us. So Ekin, thank you for joining in. It's really a nice pleasure and, honored to see you with us here too.
It's my pleasure.
So let's hear from you.
Okay, I will talk about basic design final project. Karapace.
Bye-bye. Anna Marie. Yeah, bye-bye.
Thank you very much.
Thank you so much for joining in. Thanks a lot.
Bye-bye. Can you see my screen now? I will go in full screen.
Yes, I can.
Okay, so basic design final project was to design and to construct a material system which would be later exhibited in a designated area at Central Istanbul. The main purpose was to interpret the abilities of a specific material and how small units of these materials can get together to shape a macroform. As a group of 9, we examined the capability of plywood and how plywood could be reduced to units and integrated in a systematic way to create a shell. After several different trials of materials, instead of using a secondary material to attach plywood units, we decided to use material itself as the connector. And plywood is found as 2-dimensional panels. When plywood surface got bigger in XY plane like this, it becomes bendable in Z direction. So when we rotate the plywood surface by 90 degrees in Y-axis, its section got thicker in Z-axis, so it becomes rigid. So we use this logic, and by inserting connectors perpendicular to macroform unit surfaces, we obtain 3-dimensional strength that allowed us to lock the whole system. And high coefficient of friction of plywood prevents slipping between the units. Briefly, the idea is to design a macroform that sustains itself. Karapace was designed and 3D modeled in rhinoceros, and units of the final design was produced with laser cutter. After macroform and connector units are cut, they were put together like a 3D puzzle. Like this, you can see our units here. So we had some manual trials before we designed our macroform digitally. First attempt was to have connectors with varying angles and identical triangles, which we chamfered from their corners. Since we have only 4 different connector angles and identical triangles, it was impossible to shape or control any kind of macroform. Second trial was with identical triangles and connectors that gave us hexagons having big connections in between their corners and a monotonous macroform that cannot be controlled according to the needs. And after manual trials, final method came out to be computational design of the macroform according to its environment. Our designated site had a tree from which we had the reference of our tripod macroform. Second step was to break the two-dimensional effect of the plywood. To give depth and three-dimensional strength to our macroform, we undulated the whole system. It helped the macroform to diffuse the load. And the third step was to have a macroform that sustains itself. That's when we came up with two different systems which work together, body system and spine system. Plywood is a material that allows itself to compose modular relations between different scales of units. Due to its modularity, macroform is consisted of triangles which are forming superior geometries as heptagons on legs and hexagons and pentagons on body parts. Through these superior geometries, we expand and shrunk our macroform according to the needs. Triangle body units and connector units were limited on their sizes because a plywood panel becomes bendable when its size got bigger, even they are locked with perpendicular surfaces. So maximum edge dimension was not more than 60 centimeters according to the material's behavior. Body is consisted of 130 different units and spine is consisted of 700 plus different units. Each body unit has 3 connectors on its 3 edges. With these continuous connectors, we obtain the spine system. Body units creating the macroform has a continuous edge-to-edge relation, while connectors create a continuous spine. We chamfered the triangles from their corners to reduce the overall weight of the macroform. These gaps are getting bigger towards the top of the macroform. It also had a positive effect on bearing snow rain load, and it emerged snow shadow effects. So here are relations for a self-sustaining system, edge-to-edge relation of triangles, macroforms triangles, connectors that create a continuous spine, and our void system, which are getting bigger towards to the top of the macroform. These images are elevations of the one that we built in 2013. Final project was a group project that allows us to see how collaboration works. By collaboration, I mean the teamwork between 9 of us. We had divided the tasks like case study researches, material researches, 3D modeling, digital fabrication and installation. And it was the first experience where we integrate technology to material performance studies and design a system. These are, I will show you some photos. This is from June 2013. This is from September 2013. This is February 2014 with snow on it. This is from September 2014. And here, when Istanbul Bilgi University was invited to Venice Architecture Biennale in 2018, Karapaça was selected because of its parametric design, easy to carry and easy to fabricate modular system, and the use of very common material, plywood. Before we sent Karapaça to Venice Biennale, macroform was adapted to its new site. It was scaled by 1.2 and the unit edges that got bigger than 70 centimeters were revised to prevent uncontrolled bending. It is easy to fabricate the units because plywood is a material that can be cut by laser cutter. Whole macroform can be cut in maximum 2 days. These are our laser cut panels, 9 of it. After the laser cut of the units, it is easy to transport them. Due to its parametric design, it is possible to adapt the interlocking system of the macroform. After adaptations, according to the new site, grasshopper was included to the journey to have the perfect continuous geometries. By using corner points of each triangle, Voronoi pattern was generated by grasshopper. By intersecting the Voronoi pattern with triangle surfaces, we got our new continuous connector lines. And finally, we did a mock-up in Istanbul in 1:1 scale. After the successful assemble, we fabricate the whole system once more to ship to Venice. And to assemble or disassemble, it is important to divide the whole macroform into layers. We coded each triangle and each connector according to a rule which we explained in the construction manual. And this is a page from our construction manual. Each layer is consisted of these smaller units, so we had a superior coding method for the layers as well. So our macroform became a 3D puzzle that everyone can easily assemble. For the last step, we included the shipping boxes into our construction manual. We ended up with assigning codes from the smallest units to the shipping boxes. And this photo is from Marinares Gardens. Installation was made by 5 people in 2 days, 1 day for installation of the structure and 1 day for the finishing touches. Since each step was explained in the construction manual, even the ones who are not familiar with Carapace managed to help for the installation. And this photo shows layer by layer installation of Carapace in Marinares Gardens. So this is our team. One of our neighbors was Daniel Libeskin's tower, which is here. And it was a great opportunity to exhibit Carapace at Venice in scope of Architecture Biennale. And after Venice Architecture Biennale, Carapace was fabricated once more and was exhibited at Architect at Work Expo in CNR at Istanbul. And the one we fabricated for the expo is disassembled layer by layer and assembled once more at Central Istanbul. You can see the layering systems here in this photo. And that's it. I hope you enjoyed the presentation. And here you can see a link, and this is the link from for our video that shows the whole design and fabrication process from 2013. And you can scan it. And I hope you enjoyed.
Thank you so much, Ekin.
Thank you.
It was really a very interesting experience for all of us. Just
yes.
You know, having it at the Venice at the Biennale too. And in relation to that, there is a question for you, Ekin, and for me too.
Okay.
The question for you is, how did your pavilion perform outdoors with the weather conditions during the Biennale?
I can show the photo.
Mm-hmm.
Okay, so here, like this. Actually,
we cannot see the screen.
Oh, okay.
You stop sharing.
Yeah. First, I had to share. Okay. Now, do you see it now?
Yeah. Mm-hmm.
Okay. We had some top coats on plywood panels, but because of the conditions, it gets like this. And what was the question?
It was about how did it perform outdoors? Perhaps just telling a bit more about waxing may also help the boat waxing that we use to protect it from especially weather conditions in Venice when water and humidity is concerned. In Venice there is in seasonal flow too, and this Carapace really survived that because of a very special waxing was applied onto it. So the second day Ekin was talking about was spent with that one, 2 coats or 3 coats, and each piece in here in Istanbul, while we were just manufacturing it, we also waxed them here in Istanbul too as 2 coats. And over there, when whole system is completed, it was waxed again. So I think it was quite strong in the sense that when it comes to the end of the exhibition, it was still standing there without any harm, as far as I know.
Actually, it stood 1.5 years in Istanbul as well.
Yeah. The first prototype.
The first one, yes.
We produced for campus. Yeah. it really also stay too long. And for me, there's another question. What is the benefit of teaching your design studio to architects, interior architects, and industrial designers at the same time? The reason why we just decided to have all departments together was we believe that design education and, especially at the very early year, at the very first year, should be developed from a very core understanding of what design is. And when we just proceed from that very starting point, 0 point, the scale is not the basic issue for us, for our team, because developing that logic of concerning parts and whole relations and developing a certain awareness for our environment through understanding both materials, technologies, geometries, representational medium should have a, a fundamental base for us that is being shared with all disciplines. So that's why we have, for about now 12 years, we have all departments together working. And the second benefit of that is when the students begin interdisciplinary in their first year education, they develop collaborations very much in the coming years. They join into, certain competitions, either design or interior design or material research or architectural design competitions together as teamworks, because at the first year, both projects are done as in teamworks. And, in the coming years, they begin to realize their friends' concerns too at the same time. For instance, Hazal and Yiğitalp developed, kind of a office period to their recent office. Now it was Backlab, where architects, interior architects, they work together. So it also gives them a different chance and perspective of understanding design at different scales, at different levels, as an interdisciplinary work too, or let's say transdisciplinary work too. So that's one of the benefits. So, okay. So thank you for the questions. Now we may proceed with our final presentation at last, but not the least, let's say. Yiğitalp Behram will be just presenting his work to us. Yiğitalp is also an architect, and he's the co-founder of the Rolab studio with Hazal, Hazal Yılmaz, as we have speaker here too. And Yiğitalp has a very interesting presentation, which also made us think further on the issue of this whole seminar on the wood and timber, because he is taking us to the opposite side of the whole picture, where he says that when the fabrication techniques and when the construction sites are concerned, there are so many improvements. But when we just consider the material used, especially in the construction sites, wood is some kind of a material that we need to develop our awareness and sensitivity more, and to develop that, how we may approach to this part of the construction from a perspective that Yiğitalp will be opening us, in detail through his form wax presentation. Welcome, Yiğitalp. Curious to hear from you.
Thank you. Thank you for the introduction. So yeah, I will be a bit in the opposite side today and a bit speculative, let's say. But for the first, I'm a huge fan of additive manufacturing. 3D printing technology is becoming more popular for the past few decades, and it started to increase its application areas. And these areas vary from medical industry, aircraft, education, mechanical engineering, and many, many more. But as an architect, I was more interested in the construction industry. And after doing some research, I have found the current designs are very kind of similar to each other. These are the three examples from all around the world. Like one of them is from IAC, the second one is from ETH Zurich, and the third one is from a private company from French called X3. And these guys are the pioneers of 3D printing in large scale, but these columns have something in common. They have this freedom in the vertical axis, but when it comes to horizontal axis, they are very limited in terms of geometry. And this is not the full potential of additive manufacturing from my point of view. Whereas in here, you can see the potential on the right-hand side of the frame. You can see the design from Michael Hansmeyer, which represents the full potential of additive manufacturing. Whereas in the left-hand side, we can see the columns from ETH30. And I can see the difference between one of two. And I asked my questions like, why is this happening? Why cannot we take the full advantage of additive manufacturing in construction industry when we start the 3D printing large scale? And the answer is without supports, it's not possible to 3D print complex shapes because supports are necessary. And when we think about supports in small scale, and when we make it big, we come up with formworks. We use formworks in construction industry, and they are more or less the same methodology within each other. And when we think about formworks, I started to research the formworks that are used in the world. And there are many materials, but the most common one is the wooden formworks that are used in the industry. And this is a photo from a construction site in Boston. And the design was a double curved roof system, and the MDFs were CNC. They were milled and they were casted with concrete. And at the end, these formworks were wasted. They were gone. So it's like these formworks are really expensive. It's really hard to fabricate them. And once you use them, you just throw them out. And if they're like complete walls, then you can use them 15 times and that's it, no more. So can we 3D print complex shapes in large scale and take advantage of additive manufacturing in construction industry? That was my question. And I come up with idea of using wax as a reusable support system. So FormWax is a project that will help the construction industry to overcome geometrical limitations in 3D printing. This is achieved by using wax that would act as a reusable support or a formwork, making it possible to take full advantage of current 3D printing technology. So in order to achieve this, I made a research about what kind of wax I can use. How can I achieve 3D printing with wax? And I did some material research and I decided to go with paraffin wax. And in order to increase the viscosity, I added some microcrystalline cellulose so that I can have this viscous material where I can 3D print. So in order to 3D print with wax, I had to design my own extruder. And it was not something that I can go online and buy, like a plastic extruder or a cement extruder or a clay extruder. So I had to design all the pieces by myself and come up with a solution where I can deposit this material safely. And after like a month of research and hard working, I was able to fabricate this extruder where I have full control over the deposition of this mixture. And later on, I decided to make this dual extrusion system where I can 3D print concrete and this wax mixture at the same time. And since I can 3D print these materials, wax and concrete at the same time, I decided that I realized that, let's say, I can cast them as well because I have full control over the amount of material that is deposited since I'm 3D printing. So I can open the walls and I can start casting. And this helps for me to build the fabrication protocol because additive manufacturing is a slow process compared to casting. And with this full control over the deposited amount of material that can be deposited, I can start casting these materials. And as I said, I started to build my fabrication protocol. How can I achieve such complex shapes using these materials? And I have 3 materials. One of them is the mixture that I made, the wax and microcrystalline cellulose. The second one is the pure paraffin wax. And the third one is the reinforced concrete that I'm using. And to simplify the fabrication protocol, I decided, okay, if I want to fabricate just a column, what should be my step? What do I need in order to achieve this? Just a simple column, like nothing crazy. And I need the formwork, which is the inner shell. And but just with the inner shell, the concrete's pressure would crack it and it will just explode. So I decided to just give it a safety zone. So I just made an outer shell, which is like the container, and I filled the gap with a paraffin wax, so it will support the inner shell and it will prevent it from cracking. So I just once I set up this fabrication protocol, I decided to make a case study. And the first case study that I want to do is the same one that I saw in the timber wooden formwork, the the roof from the Boston. So I decided to go with the double curved surface roof system because they are super easy to design nowadays with advanced computational tools such as Rhino, Grasshopper, or Maya. They are like super easy to design, but to fabricate, it's a bit tricky there, especially with concrete. So I decided to come up with this idea of like, I can 3D print the wax molds and I can smooth them. And then I can just cast the double curved surface. I can cast the concrete to create this double curved surface in it. And I can just repeat this and divide it into equal parts. I can just then assemble these parts together to have this. But I realized that, okay, this might work, this is good, but I'm not speculating enough. Like, what is the full potential of this technology? How can I push the limits? Then I decided to go with an agent-based design, which is almost impossible to fabricate with the classical fabrication methodologies. So I wanted to push the limits and see how can I just take advantage of this fabrication protocol that I have created. So again, there are 4 key elements in this design. I have the outer shell, which is like the container of all the system. I have the inner shell, which is the formwork for the concrete, and I have the poured paraffin wax, which is the barrier for the inner shell that it will prevent it from cracking when the reinforced concrete is poured. But in order to gain some time and to make it like more efficient, I tried to optimize the fabrication protocol and try to make it a bit faster since 3D printing is slow. So I made a support study where I visualized the parts where we need supports. And since it's a hollow structure, we need supports both in the inside and in the outside of the system, which is a bit tricky. But I call these parts where we need supports are the critical printing points where the system is 3D printed. As you can see, the outer shell and the inner shell, the wax and cellulose mixture parts are 3D printed. And then certain amount of pure wax is poured, and then the concrete is poured. This is happening because we need supports in these areas, and the system should go layer by layer because we cannot go that fast. But in the prints where we don't need supports, certain amount of layers can be 3D printed, as seen in the outer shell and the inner shell, and certain amount of paraffin wax is poured, and then certain amount of concrete is poured as well. So we can make things faster if we don't need supports. And in here, it's a bit easier to understand how it works, so that like we're having these outer shell and inner shell and filling these gaps with a lower melting temperature paraffin wax, so that the system doesn't melt and it doesn't change its integrity. And then once we have these paraffin wax casted, then we can start to cast these gaps with reinforced concrete to have this complex shape. And at the end, the idea was to have this massive block of wax and concrete, and then we can melt it, recollect these waxes to reuse them. Because if you don't burn it, you can reuse this wax as much as you want. And that's the, I think, such an, I would say it's a better version of wood, because like we're wasting wood when we're trying to fabricate things such as those roof systems that I showed. We're wasting such a good quality timber, and then we are using it just for once. Then we're just throwing it out and wasting such a resourceful material. And I made a small scale version of it using wax-based filament. I casted it with concrete and took it apart with melting. Of course, these filaments are not reusable, but at the end it worked because these parts were like quite small and fragile to remove the filament, the formwork. So it made me realize how good it can be if the system works properly, and what can we achieve in the future if the system works. So we can start to have weight optimized structures where certain amount of concrete is used and no more than needed. So we can optimize the weight, or we can have some hollow structures, again, for infrastructure or pumps or anything. So the future is endless. The possibilities are endless, basically, because with the new CAD softwares, as I said, Rhino and Grasshopper, like designing these columns and gyroids and everything is super easy, but fabricating them is the tricky part and almost impossible with concrete. So that's where I was speculating about how can we take advantage of these technologies with an environmental approach. And thank you for your attention.
Thank you, Yiğitalp. It was really very inspiring and very, very interesting topic. And I also have a kind of a question. Since you're really dealing with this construction industry, did your research or did you ever had any opportunity to, expand it to the field somehow? Or is it kind of a research at the moment?
Well, it's a research at the moment. I mean, I got in touch with Roberto Novoni. He's the head of STU Create in Denmark, I would say. They want to fund using the same technique. So they are not the industry, but the academia is right now investigating on this technique. But the academia should solve the problems, and it's not there yet to give it to the industry yet, because there are many problems that I faced with, and I was able to solve them up to a certain level because I'm not a mechanical engineer or a material scientist. So I was able to handle these problems in a certain level. So it would be amazing if a professional material scientist or mechanical engineer handles these questions.
But very interesting, and it also brings so many questions into the mind when the scale is blown up into the building scale. The kind of, I think, 3D printed formworks that you were developing to pour the wask as a pre-work for concrete formwork. So how would that be? The industry or this construction field or the engineers might be really dealing with that topic too, how to just expand that field. Okay. Selçuk says, yeah, you are taking compliments. I think it's for all of the speakers and especially for you too, Yiğitalp. It's very inspiring, impressive research. If there was a physical event, the noise of the clapping would be deafening. So thank you for all the speakers. As far as I know, we are up with the time, but if is there any questions that we may answer? We will be very glad to hear the questions at the very last minutes. As far as I can see, we have 3 minutes to go to the closing ceremony. Any questions, any comments from the audience or anything the speakers would like to add on the presentations? Since it was a kind of a panel that we try to develop from a very broader perspective of taking nature as a source of inspiration by biomimicry, and through a research by Jonas, how practice and research might both diverge and come next to each other to develop different types of design work at the same time. And then we proceed with Hazal and Ardeshir for upcycling timber, really in a very, again, interesting approach as a research project that they develop, an education site from us at the design education in the first year from Turkey from us, and Yiğitalp taking the very other side, what we may do by taking out timber as a kind of a very resourceful material to perhaps protect furthermore, how we may develop further projects to deal with that problem perhaps and save wood. So that's all, I think, for us. And thank you.